Hello, good afternoon and good morning. Welcome to our OSTHUS knowledge sharing webinar on data integration and lab informatics. My name is Melanie and I am a marketing manager here at OSTHUS. For today, I'll be your moderator. It gives me a great pleasure to have with me in this webinar Adrian and Henning, both consultants here at OSTHUS. Unfortunately, Natasha is ill. Her part will be taken over by the two consultants. A few short words on OSTHUS. We bring together experts in data science and lab informatics. We are located in Germany, the US, and in China, and our mission is to connect data, people, and organization. And before I hand over to our speakers, I would like to go over the functionalities of the webinar tool. On the top bar, you see a question mark, where you can enter your comments and questions all the time. We will answer the questions in the Q&A session in the end. If you experience any difficulties, please also use the question mark. I will try to solve it directly. The webinar will be recorded and we make it available through our social media channels afterwards. Let me now hand over to Adrian. Adrian, it's now you.
Thank you very much, Melanie. Let's start by taking a look at the agenda for today's webinar. We will talk about data warehouses, of course, and we will start with the introduction into why data warehouses are out there, what the purpose is. In the next part, concepts, we will talk about the definition of data warehouses and the different approaches of building them, because a few established processes exist. Afterwards, we will look at a specific use case from the pharmaceutical domain, and then we will also take a look at what one can do once a data warehouse is in place, because then analytics can be performed on top of the data warehouse. And we will close the session with a summary. So right now, let's go into the introduction. We work primarily with life science R&D companies, and we often see that there are issues with getting insight from the data, because data are scattered across multiple source systems and stored in silos. This can be, for example, that different departments use different software applications to organize their data, or, for example, in different continents, like in Europe and the US, different tools can be used for the same purpose in the laboratory, for example. Sharing between these separated systems is challenging, and out of the box, oftentimes the data cannot be analyzed in an integrated form. That's where data warehouses come into play. Also, there are obviously multiple vendors and technology stacks in use which separate the IT landscape in the environment. As I mentioned, data analytics in such an environment can be difficult. Oftentimes what we observe when we come into a company is that people manually integrate data using Microsoft Excel, for example, and this is time-consuming, prone to errors because of the large number of manual steps involved, and also the amount and the extent of analysis that can be performed using that is limited. So this motivates why we use data warehouses, or why there are data warehouses out there, because such a data warehouse can overcome these system boundaries and can provide a integrated storage location where data from various source systems can be integrated. Also, an advantage is, for example, that in a corporate environment, applications can be retired when a data warehouse is in place. Think about, for example, a LIMS system that has come into age and that is supposed to be retired. If you have stored all the data from the LIMS system in an integrated data warehouse, there is no problem with retiring the LIMS system and putting a new into place, which also then feeds data into the data warehouse, because the data is separate from the source system. Also think about mergers, for example, where you can add additional data sources and integrate them into existing data warehouses. These are all usage scenarios where data warehouses come into play. Next, let's take a look at concepts for data warehouses. So first, here is a definition of a data warehouse. There are quite a few definitions of data warehouses out there, if you do a web search, for example, but this, we believe, is one that is straight to the point and easily understandable at the same time. Because according to this, a data warehouse is a storage architecture which is designed to hold data and metadata extracted from data sources and to provide these in an aggregate form which is suitable for analysis according to business needs. So there's essentially two main parts in this definition. The first part aims at the data integration, so getting data out of the source systems and putting it into an integrated form. And the second part actually has a focus on the analytics which is performed on that. And that's actually important because while the data warehouse itself is an architecture to make the data persistent and to store it, the way in which that is done and in which the data is integrated, that is defined by the business use cases, so by the analytics that is later on performed on top of this. So moving on. Next slide. The data warehouse is therefore in between the data sources and the business intelligence reports. So data are extracted from data sources, and in this pictogram you can see that can be a vast number of different types of sources like relational databases, but also file repositories and so on. And then from the data warehouse, analytical tools can be used to analyze the data and to gain insight. And again, there is a large flexibility because you have this central data warehouse, but the type of data sources and the type of business intelligence tools that you use together with it, that's very flexible. And we at OSTHUS, we have experience with semantic technologies, and we have also built semantic data warehouses where we extend the capabilities of traditional enterprise data warehouses by semantic technologies. So that means that additional links and additional information becomes available, which is normally not there out of the box. Looking now at the history of data warehouses. In this historical overview, you see a timeline which ranges from the 1970s to now and to the future even. Back in the 1970s, when SQL was developed, IT systems relied on centralized storage. And that has changed since then. So today we live in a world of big data where a lot of different devices generate but also consume data. That has changed the focus, and as you can see also in the timeline, in the 1980s we observed the first data warehouses being reported, and later on in the 1990s and 2000s, two names come up, which are the names Inman and Kimball. And these are the names of two pioneers who have developed data warehouse modeling approaches, and their names are today synonyms for these two modeling concepts that are still both relevant. So both the Inman and the Kimball data warehouse are still very relevant to today's data warehouses, and we will learn a little bit more about that in the following slides. Since the 2000s, the semantic technology becomes more and more important, and it is also integrated in data warehouses more and more these days. More recently, the term data vault has come into play, and that is yet another modeling technique for data warehouses, which aims to combine some of the advantages from the Inman and the Kimball data warehouse, and also about this we will learn a little bit more in a few moments. And now, and also we see that it is becoming more and more important, the term of virtual data warehouses pops up. So a virtual data warehouse, in contrast to a classical business data or enterprise data warehouse, is a data warehouse which does not have a persistence layer, but can dynamically integrate data from sources and make it available for analytical purposes, which obviously has some advantages, because when using a virtual data warehouse approach, it's possible to work very dynamically, very agile, and to react quickly, and to also quickly have something in hand, have the data warehouse in hand. But there are also certain disadvantages, because especially with regard to performance, there are certain limitations, because data warehouses, especially today, can have large amounts of data in them. So ranging to many terabytes, even petabyte ranges, that's possible. And doing that in a completely virtual environment, of course, poses a tremendous stress on the technology, and also limits the complexity of data aggregations and modifications that can be done. 3 terms are mentioned here on top of the timeline. That's volume, velocity, and variety. This is also referred to as the 3 V's or the 3 Y's of big data, as defined by Gartner many years ago. And that illustrates that the volume, so the sheer amount of data that IT systems and in particular data warehouses have dealt with, has increased tremendously over the past years, as I also just illustrated by giving you some ideas of how large a data warehouse can be. Velocity illustrates the rate at which data comes in. So today that's very different compared to the 1970s and 80s, obviously. So a lot of devices generate data, and some data warehouses are updated many times a second with new data, and there's different use cases, obviously, for data warehouses which operate on real-time data, and then others which do not. But also about this we will learn a bit more in a few moments. And the third Y is the variety. So this illustrates that today, in a typical enterprise environment, we are looking at many different data sources, also different types of data sources. It can be relational databases, but it can also be file repositories or APIs like RESTful web services, for example. And this creates challenges, because all this data needs to be integrated into a single platform, the data warehouse. Here on this slide, I'd like to compare 3 data warehouse developments or concepts. On the left-hand side with the classical data warehouse. These rely on structured data and on relational databases, and both the Inman and the Kimball data warehouse, which we mentioned briefly earlier, they fall into this category. The data vault modeling concept that was also mentioned briefly, that's utilizing a hyper-normalized database, and that means that it is easier to for IT systems to process the data in there, and can even be automated to some degree. Then on the right-hand side, a term that always comes up when dealing with data warehouses is the term of data lakes. And this is a very different approach where all the data are captured regardless of where it comes from or what format it is in, and therefore it is also suitable for unstructured data, like think files, for example, PDF documents or emails, something like that. And that is a trend that becomes more and more important, and that we see more and more often. However, there's also a danger in this, because on the one hand side, it is easy, or relatively easy to capture all the data in a data lake. But then if during the data capture process, one does not think about how to analyze and what to do with this data, then later on, when something is supposed to be done with the data in the data lake, problems can occur, such as that it is not clear what different files that were loaded mean or what the context is. So in a data lake, it is very important to capture the right amount of metadata in order to make sense of the data that is stored in the data lake. Otherwise, it's just data hoarding, and there's not much that can be done with it afterwards. Nevertheless, it has its place, and just to take up the data and to store unstructured data, this is a very useful approach. All these three developments that we distinguish here have in common that they persist the data in a core data warehouse that is mentioned here, and the data originates from data sources, so that's mentioned as data input here, and then the data is also provided as an output for some sort of analytical effort, for some BI application, for example. So now I'd like to compare the term data warehouses and data mart, because that's also something that always comes up when talking about this topic. And oftentimes these two terms, data warehouse and data mart, are used as synonyms, but I'd like to make a distinction here and tell you what the difference is. Let's start by looking at the main purpose of a data warehouse. Data warehouse is supposed to be an independent and integrated data store. It provides historization, and it is the basis for business analytics. All these three purposes are fulfilled by a data warehouses, but only the third one, being a basis for business analytics, that's fulfilled by a data mart. And looking at the two concepts side by side now, the difference becomes even clearer, because data warehouse usually hosts company-wide data from multiple subject areas, so it's wide, whereas the data mart oftentimes is purpose-built for a specific purpose and therefore has a very narrow focus. It consumes data from a single subject data, typically from a single department as well. As a result of these conditions, the data warehouse has a relatively complex structure, whereas the data mart, in comparison, is relatively simple. And the last row, you can see that as a result, the data warehouse can also support many different types of analytical questions, present and future, because the data is stored in a generic, standardized form. Data mart is built as a means to an end, and therefore normally can only answer a specific business question or a range of business questions that were defined when the data mart was built. Of course, data mart can be extended, but the point is that a data warehouse does not have to be extended to answer new types of questions, but just the extraction of the data maybe has to be modified a little bit. And the illustrations that you see here on the side, they also symbolize the difference in complexity. On the left side, the hypercube, where you have a lot of different details integrated into a structured form, possibly with semantic technology as well. And on the right-hand side, it's relatively simple. You have one question in the center, and then you have some data around it which is connected to this data. Also, a data warehouse can contain data mart. So a data mart can exist on its own, but it can also be a part of a larger data warehouse structure. As we will see in a minute, data warehouses can hold all the data, but the data may not be available for analysis easily. And then it's possible to build a data mart on top of the data warehouse, which extracts data from the data warehouse and then aggregates it further or brings it into a form that is suitable for analytics and then provides it as output. So, as promised, let's now look at two established methods for building data warehouses, and I'd like to go over the advantages and disadvantages as well. I mentioned earlier the pioneers Rolf Kimball and Bill Inman. Their names are synonyms for these two modeling approaches. On the left-hand side, the Kimball utilizes a star schema or snowflake schema. It can also be a snowflake. On the right-hand side, however, the Bill Inman approach is an entity relationship model. And that means that, as also illustrated by the visualization, the data is normalized in the third normal form, whereas on the left-hand side you have it connected by more by meaning. So that's what dimension and facts means. The approach for designing these is also very different, because the Kimball data warehouse is built by having the data marts first. So the idea is that in a corporate environment, various data marts are built for specific business cases, for business questions, and then at the end, all these data marts can be integrated into a larger structure, and that then is a Kimball data warehouse. The Inman data warehouse is different, because here you would not start building individual data marts first, but you would define a common data model for the whole enterprise, or at least for the whole data that should be integrated. And then the data is retrieved from the source systems and loaded into the data warehouse. As a consequence, for the Kimball data warehouse, which is built by building data marts first, you will not need additional data marts, because the data marts are already there. The data warehouse is essentially the sum of the data marts. And therefore it's quicker to build, but it's also difficult to maintain, because you have a large range of difficult data marts, and they are existing side by side, and they may or may not be possible to integrate them into each other easily. The Inman approach on the right-hand side has a larger effort upfront for designing and building it, so it's more time intensive, but you will not have to build the data mart first. But the downside is that after integrating all the data into this large data model, you will have to build data marts on top of the data warehouse. So what does that mean? The data are integrated into the data warehouse, but they are stored in a form that maintains their integrity, but not necessarily in a form that is suitable for the analysis. And therefore, the data has to be extracted from the data warehouse and brought into a form in these data marts, which work on top of the data warehouse in order to make them available for analytics. So these are the two approaches, and both of them are very valid. Both of them have their place today, because they have their own advantages and disadvantages. The Kimball data warehouse on the left-hand side is very easy to, or quite quickly to build, at least in comparison to the Inman data warehouse on the right-hand side. And one can start with what's already there, because oftentimes there are already data marts in place. And here are two quotes from Kimball. Kimball says that the data warehouse is nothing more than the union of all data marts, which also corresponds to the definition that we had just earlier. And in contrast to that, a quote from Inman says, you can catch all the minnows in the ocean and stack them together, and they will still not make a whale. So that implies that the data warehouse is not just the sum of its components, not just the sum of its data marts, but that it adds something on top of that. So it's a different thinking that's behind that. But depending on the use case, both of these can be a good choice. Here, the concepts of data warehouses a little bit in more detail. In general, you have data sources on the bottom left-hand side. As mentioned before, this can be from the various data sources like relational databases, file repositories, APIs, and so on. Those get loaded into a staging area inside the data warehouse that you see here in the orange box, and then move into the enterprise data warehouse. The way in which this works is typically that data is copied directly to the staging area to minimize impact on the source systems, and that then a process which is abbreviated as ETL starts, and ETL stands for extract, transform, and load. And this process takes the data from, in this example, the staging area, transforms it, so it brings it into a shape that is suitable. For example, data curation can be performed as a transformation step, or data validation, or aggregation, and then the loading takes place, so the data is deposited somewhere. In this case, in the first ETL process that is listed here, data will be loaded into the enterprise data warehouse. The enterprise data warehouse can again be divided into a raw data warehouse and core data warehouse, where different tasks are performed, but we will not go into detail into this at this point. And then again, after the data warehouse, there's a second ETL process, or actually there are two arrows here, so two possible ETL processes, and they feed data into two data marts. And that tells us that we are looking at a Bill-Inman data warehouse here, because a Kimball data warehouse would not have separate data marts, but the whole data warehouse would actually be a data mart by itself. And from these data marts, the data can then be used to perform analytics with a wide variety of applications. And to give you an understanding of what the E and the T in the ETL process mean, the extraction can be performed in various ways. For example, as a full data load or as an incremental data load. For large data warehouses, it doesn't make sense to load all the data with every refresh of the data warehouse, but then an incremental data load is performed. So only the data that are new or that have changed since the last refresh are retrieved and processed. And here are some examples for what can be done in a transformation step of the ETL process as well. Next, we will take a look at a typical use case from the pharmaceutical domain, and for this I will hand over to my colleague Henning.
Thank you, Adrian. So before we look for a specific example or use case, let's just have a look at the typical advantages or disadvantages of such a system. One thing which is already mentioned is that it brings together different data sources from different source systems, and it allows to compare or correlate data from these systems. It has a centralized staging area for data curation and data enrichment, and it is designed to improve querying of data, especially with respect to the performance. Also, a data warehouse usually is independent of business intelligence tools and allows you to use any customized solution. You could use standardized tools or whatever you like on top of it. So at the end, it answers a number of questions which you probably would not, cannot raise that easily without using such a system, because it allows you to cross system boundaries. So it's time saving. On the side of the disadvantages, you see that the implementation effort can be quite high, depending on the level of customizations which have to be made and the number of systems which need to be integrated and so on. So there's another system which you also have to take care of. So maintenance and administration efforts will be also on the side of disadvantages. Another point is that due to the source systems, data warehouse requires regular loading from the source systems. When data changes at the source system level, you will have to integrate the new data into the system as well. This one is taking account of with the changed data capture mechanism. Now, when we look at some scientific use case, probably in the pharmaceutical industry, you could imagine that there are different domains where you want to have data integrated from. For instance, there would be compound synthesis. You might have a compound registration system where you want to integrate the data from. You probably would have data from in vitro pharmacology, data from assays you run in the test tube, so to speak. And also possible that you want to see data from in vivo studies, preclinical studies. So that could be, for instance, that some tests with animals have been done and you want to see the results there as well. And finally, as another option would be formulations. So collecting recipes or how to manufacture the actual product for your company. So everything here is predefined by the existing source systems you want to integrate. As already mentioned, it allows you to trace all the different parts going from the synthesis of compounds over the development, over compound storage and logistics, up to biological activities and the outcome of findings from assays and tests you do. So you can correlate experiments from different fields. Now I want to show you example implementation for such a case. So we start with a number of source systems you probably have. So that could be many different technologies which come into place. For instance, you could have relational database systems. Another option is that you have a document management system where you want to retrieve data from, or you have a web service which delivers data. So the first step is that you have a staging area. Usually here it's indicated by the blue box. Usually this is a relational database system then. So the first step on the left-hand side of the blue box is that you load the raw data via an interface into interface tables. You could imagine that certain systems could also have a journaling table which allows you to trigger and to find out which data have recently changed in the source system. So that allows you to do a data capture or data management and avoid loading everything from scratch again and again. In the central part of the blue box, you see that the data needs to be aligned. This is part of the data normalization. Here, usually one is selecting a property which is relevant for all the different source systems and is somehow also part of the queries or the questions you want to raise later when analyzing the data. So for a typical pharmaceutical example, that would be, for instance, a compound-centric system where you use the compound as reference link between the data. So within the next step, the transformation, which is done up to the right-hand side of the blue box, you will bring the data into a hierarchy. So you have different levels, starting from the top parent level, going down child level, subchild level, and so on. In a compound-centric view, maybe, for instance, you want to have a parent compound structure on top. And the following hierarchy level would be then maybe the compound, followed by a batch level, and then going to experiment, and finally the result levels. So from every hierarchy level to another, we have some sort of 1 to n data dependency existing. In the next for the curation of the data, it is good to introduce an administration layer. Here, a data steward can, for instance, define filters or flow control, introduce a controlled vocabulary to influence the way the data are transformed. In the next part, usually we have another database scheme where we build up the actual data warehouse, which is query optimized. Here again, we keep the hierarchy from top to bottom, but we introduce satellite tables. These are based on functional assignments. That means, for instance, that you group data according to questions or specific functional assignments you make. For instance, you could imagine in a pharmaceutical data warehouse, you would have on the compound level different satellites. One, for instance, telling you something about in silico computed data for a compound. On a batch level, you could furthermore introduce, next to experimental phys-chem data, you could introduce data about the logistics in a separate satellite. And for the experiment or result levels, you would have aggregations or satellites for each of the different fields you want to query, for instance, ADME data or toxicology data. So this leads to this type of snowflake structure, which is shown here. Optionally, you can also introduce aggregation on the different levels of this hierarchy. That means, for instance, that you want to aggregate over different batches where you want to know for a certain result type, mean value, standard deviation, and so on. Aggregation is or can also be defined in the administration layer by defining aggregation rules. The next step is that probably the user don't want to look to the naked database scheme to see the data and to query those. So usually you introduce a GUI layer in between where certain applications or BI tools come into play. This could be, for instance, Spotfire. This could be .matics browser or different other tools. So you have this additional layer where the user accesses the system and where you also define the access rights of different users. For instance, these applications also allow to define most commonly queries in the type of forms and present these data in a specific form to the user. So that is basically the use case example we wanted to show here in this session. And for the next part, I will hand over to Adrian again.
Yeah, thank you, Henning. Now we will talk about analytics. Analytics is what the users interact with, because they typically cannot see the data warehouse. When they use a business intelligence report, to them it looks like they are working directly with the data from their source systems. And that's exactly also the idea, that the data integration happens in the background and is not visible to the end user who uses the BI report. The BI report has the purpose of providing the user the opportunity, the option to see their data from the source systems. And they see it in a way that they cannot do with the source system directly. For example, because the data are distributed across multiple systems. Think about an ELN system and a LIMS system, for example. They may both contain data which are relevant to answer a specific question, but they are stored in different systems and the analytical capabilities of the respective source systems do not allow them to cross this border between the IT systems. So then with the data warehouse bridging these two source systems, they can then analyze data across these source systems in a way that before was not possible or required extensive manual data integration. As a result from this, they can then understand the data and correlate the data with one another and draw conclusions from it. And this insight then leads to action, so they can act on it and make the right decision. From our experience, the process of building a data warehouse and also the business intelligence reports, which in our experience are an essential part of the data warehouse, should be done in an agile way, as illustrated here. That's because oftentimes the data warehouse is not built just because a data warehouse is supposed to be built, but the driver is very often that analytical actions should be performed on top of it. And therefore, what's providing value to the users is actually the BI report, the business intelligence report, which utilizes the data warehouse in the background, but as mentioned before, that may be not visible to the users because they just see the analytical part, and also they often just don't care how the data are integrated as long as it's available in the correct form. So this data warehouse part is in the shadow behind the BI report, but the feedback that we get from the users is usually aimed at the business intelligence reports. For example, they have certain questions that they want to answer, and to answer those questions, they need data from multiple source systems, for example. So then, based on this information, the data model for the data warehouse is either created or modified, and the data warehouse layer is built, and then the BI report on top of that. But then the important agile component is that then the users are involved in the refinement of the construct, and that their feedback is used to modify the data warehouse and then also the BI report. Here are some typical questions that we are dealing with in our chemical and pharmaceutical customer domain. For example, in a pharmaceutical company, the question should be, which compounds could become drug candidates? Very wide question, but in order to answer it, the data which are associated with specific compounds need to be visualized in some way. And this data may be distributed across multiple systems, like an HTS system, for example, a LIMS system, which houses analytical data, and so on. Another question in a laboratory environment could be, how many samples are currently open? So that's more of a KPI question, which can be answered with one number, but here it could be a question that has to be answered on real time, because the user is not interested how many samples were open yesterday or this morning, but this number may change frequently. Other questions in relation to this might be, how long is a sample typically open on average in a laboratory? Kind of things. In a regulatory environment, a question could be, how many overdue variations are there, or where they are? So maybe they are in a particular country or a particular region geographically, and then this information is available in a table somewhere, but to visualize it with the right way, in this particular case maybe with a map view, that provides a cohesive answer for a user who has this particular question. These are just 3 example questions. One can think of many more, of course, but they all can be assigned to one of a few categories which are listed on the bottom here. So that could be pattern analysis, for example, with regard to demographical or geographical categories, for example. That's the example with the regulatory earlier, where variations are in certain regions geographically, and one is interested in comparing these different categories. Another question category would be optimization problem or decision support system. That's more in line with the pharmaceutical question example that was listed before. So really bringing all the information that is available for a specific entity, like a compound, for example, and then providing the user with all the information that is required to make the conclusion and how to proceed with this particular compound, for example. Then there are real-time data analysis questions. How many samples are currently open, for example? Another question category would be predictive analysis. So in a laboratory environment, the lab head could ask also how many samples are typically submitted on a Monday or on a Tuesday. Maybe it's not the same on every day of the week. Or based on the existing data, how long does it take to close all the samples that we currently have? That goes more into the direction of prediction. Also, one can include more extensive statistical analytical tools such as R into the tool stack and have a real statistical analysis be performed on top of the data. Another point would be text mining, for example, which could maybe be relevant for regulatory, where you get PDF documents which contain text which you want to search, or if you want to, for example, perform some linguistic analysis to determine the language of a document, those kind of things could also be relevant. That brings me to the summary. So let's summarize what we presented to you today. We explained to you what data warehouses are, why we have data warehouses, and what benefits they can provide to a business. And in essence, the benefits are that they can enable you to perform and to do new analytics, and also to do them much quicker than before, because doing it in a manual fashion is time-consuming and can lead to errors because of all the manual steps. So especially when you think about validated environments, having an automated workflow to perform analytics is a big advantage. Data warehouses can help you to overcome data silos and system boundaries and integrating the data from multiple systems into a single data repository. And another aspect is historization. You can integrate the data and maintain the history and the changes that happen. So you can, for example, ask the question to a data warehouse, what was the answer to a particular question 1 year in the past or today, and how did it change? That is a question that you can not typically answer with operative systems, because they either don't store the change of data at all, or only in a limited way. And another aspect that we briefly touched was that value can be added to data warehouses through the use of semantics, by building up links which enrich the data to allow you to answer even more questions and have more information available than you would without the semantic integration. And that brings me to the end of the presentation, and now the floor is open for questions. So if you have not submitted them already, feel free to click on the question mark icon on top of the screen and send your questions. Melanie, do we have questions?
Yes, I already see a question coming in from the audience. And as Adrian already said, please use the question mark to send in other questions. So here the question I have is, what would be a typical technology stack for a data warehouse? I think, Henning, that could be a question for you.
Yes. So from our experience, what we do is usually we start with a relational database for staging and the actual data warehouse. So that could be, for instance, an Oracle database or any other SQL database, you could use like Postgres or MS SQL. As an ETL tool, there are different possibilities. There could be Oracle Data Integrator, that could be Talent, that could be Informatica. And you could imagine that you could use different BI tools on top of the data warehouse, like from PerkinElmer or from Dotmatics or any other system, which analyze the data and allow reporting or querying of the data.
Okay, thank you very much. I have one more question here from the audience, and it's regarding data vaults. I think that one could be one for you.
Okay, let me see. It's about the hypernormalization part. Yes, okay, maybe that wasn't explained clearly. Data vault is a quite new development, became more and more popular in the last years, and we see it more and more often. And the hypernormalization, that's one of the characteristics of the data vault. That means that the data are normalized even more than they are in an Inman data warehouse. The Inman data warehouse has the data already in a third normalized form, and in a data vault, the data model would be more normalized in the sense that the dependencies between the different entities are also stored in individual tables. So the entities themselves, which are called hubs in the data vault, and the links between them, and also the information which are stored for the hubs. Those are stored individually, and therefore the information is scattered over multiple tables, which makes it a little bit more difficult for the human to understand, but this has some advantages when thinking about automated processing, because computers can deal with this information in a more efficient way.
Okay, thank you, Adrian. I think that is all from the audience right now. So if you don't have any more questions, I would say that is all we have for today. Perhaps a short remark. As I said in the beginning, the webinar will be recorded and we will make it available on our social media channels afterwards. So I want to thank you, Adrian and Henning, and everybody who joined us in the webinar. Thanks for attending. Have a good day. Have a good evening.
Thank you.
Bye.